Deep learning engineering operates on a harsh paradox. Modern GPUs possess phenomenal compute power, easily capable of performing trillions of operations per second. Yet, when we write standard, high-level code, we constantly starve that compute core of data. The processor spends the vast majority of its time idling, simply waiting for data to travel across the chip. To understand why, look at the physical reality of a modern NVIDIA GPU. The central die is packed with over 100 individual processing units, called streaming multiprocessors, or SMs. Zooming into a single SM, we find a strict memory hierarchy. The fastest memory formats, registers and shared memory, reside directly inside each local SM. They sit right next to the compute cores. Surrounding all of this is a massive outer layer, the high bandwidth memory, or HBM. The distance between these memory pools dictates performance. Accessing data from local registers or shared memory is almost instantaneous. But fetching a single element from that distant HBM warehouse can take hundreds of clock cycles. Achieving peak hardware performance is rarely about doing the math faster. It is strictly an exercise in keeping data local to the SM and avoiding the HBM bottleneck. Because of this latency, the unbreakable rule of systems engineering is that you must measure exactly how your memory behaves before you attempt to optimize it. You benchmark to see how long things take, and you profile to see exactly where that time is spent. When you profile standard PyTorch operations, the hardware constraints become visible. Standard operators process data element by element. For every step in a mathematical sequence, the code reads from HBM, calculates the result, and writes the intermediate step back to HBM, forcing redundant round trips for every single operation. This chart compares a naive PyTorch GELU execution on top against a compiled Triton kernel execution on the bottom. The PyTorch method is fragmented, relying on multiple kernel calls to process the same data sequence. The compiled version executes as a single block. That compiled version fuses those operations into a single custom kernel. It pulls the data from HBM once, performs all the necessary math entirely within the local SM, and writes back to HBM once. By eliminating the intermediate trips, the arithmetic intensity, the ratio of compute operations to bytes transferred, reaches a point where the chip is no longer throttled by memory latency. To capture the hardware's actual throughput, engineers must break out of PyTorch abstractions and manually dictate memory flow using custom Triton kernels. When writing custom kernels, you have to map your code to the physical execution hierarchy. At the lowest level, individual threads do not act alone. The hardware groups them into sets of 32, known as warps. Every thread in a warp must execute the exact same instruction in absolute lockstep on every single clock cycle. This hardware design creates a trap called warp divergence. If you introduce an if-else branch into your code, the warp cannot split up. The execution is sequentialized. It runs the if path while the else threads idle, then swaps. You instantly cut your processing efficiency in half. Moving one layer up, multiple warps are grouped together to form a thread block. This is the primary unit of compute that the GPU scheduler assigns directly to a physical streaming multiprocessor. Even when threads operate inside a block, they must follow strict physical rules. For instance, to utilize HBM efficiently, adjacent threads must pull data from contiguous memory addresses, a requirement called memory coalescing. If threads ask for scattered addresses, the GPU still fetches full 128-byte cache lines, wasting massive amounts of bandwidth. Inside the SM, shared memory is divided into 32 separate banks. If multiple threads attempt to access the same memory bank simultaneously, the hardware cannot process the requests in parallel. The accesses are serialized, creating a bottleneck known as a bank conflict. High-level kernel languages provide clean abstractions for writing math, but if the code you write ignores these physical hardware quirks, divergence, coalescing, and bank conflicts, the physical chip will throttle your execution speed to a crawl. Triton is a programming language designed to operate precisely at this thread block abstraction level. Instead of coding what every single thread does, you define what an entire block of threads will do together. Take a simple element-wise operation like a GELU activation function. You start by identifying the block. The thread block wakes up and uses its assigned ID to calculate an offset, determining exactly which segment in the massive data array it is responsible for. Once the boundaries are set, the block loads its specific data vector from HBM into the local SM. It applies the mathematical activation function to the local data and stores the completed output vector back to HBM. While this reads like high-level Python, the Triton compiler translates this logic down into PTX, parallel thread execution. This is the raw, low-level assembly language that dictates exactly which registers and instructions the physical GPU will use. By handling the load, compute, and store phases in a single defined kernel block, you guarantee no intermediate values are ever written back to HBM. Element-wise math is straightforward because elements don't need to interact. Complexity arrives when operations require data aggregation. Consider softmax. To calculate the probability distribution of a row, the math demands that you scan the entire row to find the maximum value, and then sum the entire row to calculate a normalization constant. The threads have to communicate. In Triton, you handle this by ensuring your thread block encompasses the necessary data. The compiler maps exactly one full row of the matrix to one independent thread block. The block reads the entire row from HBM into its local shared memory. Because all the threads within this block share that local memory pool, they can rapidly calculate the maximum and the sum together, apply the normalization, and write the finalized row back out. Containing the row completely inside a single block is critical. It allows all communication to happen inside the fast local memory, completely avoiding the severe latency penalty of synchronizing data across multiple physical SMs. But hardware dictates strict physical limits. A single thread block on modern hardware can typically only hold 1,024 threads. If your data row is 4,000 columns wide, the row no longer fits inside the block. When data exceeds local memory capacity, you implement chunking. You slice the massive row into manageable tiles that fit the block size. You still assign one thread block to process the entire row, but now you must explicitly program a loop. The block will process the data iteratively, cycling through the tiles one by one. Inside the block, each individual thread maintains a running accumulator, a variable stored in its ultra-fast local registers. The thread reads its assigned element from tile 1, adds it to the accumulator, then moves to tile 2, adds that value, and repeats until the row is complete. Once the loop finishes, you have 1,024 individual thread accumulators. The block performs one final local reduction sum across those accumulators to yield a single scalar value, which it writes out to HBM. When data scales beyond physical hardware limits, you can no longer rely on automatic abstractions. You must dictate the loop and manage the accumulators explicitly. This brings us to matrix multiplication, the core operation of deep learning. A naive approach here is inefficient. If you compute an output matrix element by element, you are forced to reread the same rows and columns from HBM repeatedly, driving your arithmetic intensity down. The ideal solution would be to load the entirety of matrix A and matrix B into shared memory exactly once. But for transformer scale models, these matrices are massively larger than any SM cache. We resolve this by applying the chunking concept in 2 dimensions, matrix tiling. We break the output matrix, matrix C, into smaller square tiles. In Triton, you assign a single thread block absolute responsibility for computing just one specific output tile. To calculate that tile, the thread block runs a sliding loop. It iteratively loads a small tile of matrix A and a small tile of matrix B into shared memory. It computes the dot product of those local tiles, adds the result to its local accumulator, and slides to the next pair of input tiles. Because the result is still sitting in local shared memory as an accumulator, you can implement kernel fusion. You can mathematically apply an activation function, like a ReLU, directly to the final values right there on the SM before executing the final write-out to HBM. Tiled matrix multiplication maximizes local compute cycles while aggressively starving the HBM of redundant tasks. Designing state-of-the-art AI architectures requires recognizing that deep learning is a physical exercise in memory management. We evolved the kernel from simple element-wise operations to row reductions, to iterative tiling, and finally to the complex tiled accumulators required for large matrix operations. Triton gives you the thread block abstraction to make this manageable, but the code you write still executes on silicon. You are always responsible for respecting hardware limits like register counts, SM occupancy, and memory coalescing. Understanding the theory of data movement is just the prerequisite. Now you need to implement it. To translate these concepts into working code, head over to the Learn by Doing with Steven YouTube channel, where you'll find step-by-step hands-on tutorials for writing custom Triton kernels. And to stay updated on the engineering reality behind the latest AI infrastructure, subscribe to the Steven Data Talk podcast, streaming now on YouTube Music and Spotify.